the first time, what that means really is, I mean, okay, so where did I leave you last time? I took a look at the quantum, not quantum, quantum harmonic oscillator, right? And then I got to the point where, was it this one? Kind of realized that what was the most interesting for me was really not covered in here, which is how is the Schrodinger equation solved, right? Like how are these energy solutions found, and that kind of means you got to solve the Schrodinger equation, which is a differential equation. And I've never done that anywhere. So just for background, I did like so my highest degree is what I did is I did a master's in computer science, and guess what? Somewhat we never even had to touch this topic, even in like the advanced math class and stuff like that. Which is kind of surprising to think about it. We didn't do a lot of physics either. I mean, I just had like an introductory course at the very beginning of my bachelor's, but there was really not much more to it. And then in high school, obviously, I mean, I say obviously because at least that's the system in Spain. Like you get to derivation and integration, and that's it. If you get there, like you can consider yourself lucky. Um, so yeah, so that's where I am at. And to be honest, when I say it from the first time, it's not that I haven't heard or seen differential equations before. I have, but I've never like really fully dived into these yet. Actually, even just done any of them. So I remember watching some videos from Three Blue One Brown where he does touch some of the topics, and then I did watch yesterday as well a couple of the Khan Academy introductory videos. They're really really good. So in the Khan Academy videos, the introduction, the stuff that I watched was the sort of the basic concept introduction, and then the one about how to solve. So there was one thing that actually helped me a lot, which I think this is what I'm going to try to do or investigate today a little bit more, which is different techniques of solving them, right? So and the videos touched upon two techniques. One was the how do they call that? They call the gradient field or something like that, a slope field, something like this. Is that a thing? So the slope field technique, yeah, exactly, where you kind of draw these, you draw these things. Yeah, I think that is probably this is the video that I watched yesterday, slope fields. And then prior to that, there was another video about solving differential equations, assuming that like a linear function is a potential solution. Um, so basically, assume the solution has a generic shape, like a times x plus m, right? Like of a basic linear function, where you just have like an x as a variable, then a multiplicative constant, and then like an added component, like a plus m, whatever other constant in there. And then you try to solve for these. So you turn the differential equation problem into a into an normal equation, I'd say, right? So if you have, just as a dummy example, if I remember this well, right? So if you have, say, something that looks like this, right? The derivative of y with respect to the derivative of x, that's awful. I gotta calibrate this better. Equals, oh God, equals, I don't know, I'm just gonna make it up, right? But like whatever, y divided by x, I don't know. Right? If I tell you that this has a y as a function, right? Y is a function of x. This has a solution that looks like this, a times x plus m. Then you kind of can plug these in here, right? You can also do the derivative of these, which is then obviously just a, right? And you kind of plug it in here. So you say a equals, and then you kind of have a x plus m equals x, and then you kind of try to solve for a, um, Yeah, something like this. I don't know. So kind of like, you turn that problem into a simpler one. So that was the other technique, which I think maybe this is what essentially you can do to solve the Schrodinger equation, because in what I think is, so the Schrodinger equation, right? You solve for the wave function. Um, Now a wave function, I think the wave function has a representation that is um, with, as a function of cosine and sine, right? Wave function, I think so. Wave function, sine, cosine. I think there's like a sine wave formula. Sine wave. So wave function, the trigonometric wave function, maybe this is something like that. Determining wave functions with trigonometric expansions. That's okay. Because that would be a trick that you could use. Like after seeing that video, that kind of clicked, right? I said, look, but I'm missing the. Okay, that's classical waves though. That's classical waves. Quantum wave function. Um, trigonometric expansion. Like if you could make that assumption, they could solve for something. In quantum mechanics, is there a relationship between the amplitude of the wave function and the trigonometric sine function? Too long to read. Maybe in some small examples you can do that. This is an expansion of two previous questions I had before. I'm now encountering a problem with an integral. We want a general expression for the probability of finding E. We have the expression for the wave function for the particle in the box. Okay, so there is. So in the case of particle in the box, which is a specific example, which might be simpler than the quantum harmonic oscillator, and maybe I should just do this instead of the other one. So you have this form, right? So you could use that identity to solve the Schrodinger equation. I don't know if that's what's done. Hmm. Hmm. But yeah, so that's an idea. But today I wanted to kind of put that aside and really focus on just the pure mathematical concept of the differential equations and kind of explore a bit more the different techniques that there's to solve. I wanted to explore, how can I use things like SymPy and maybe Mathematica or something else to kind of like, do these maybe numerically or with a computer or something like that. Um, because at the end of the day, it's good to know, of course, how to do these by hand and all that stuff. But I think that kind of high level techniques are interesting. But then at the end of the day, if you want to be realistic, why not use a computer, right? Um, so I think it just helps you to understand the core concepts. Definitely, it's helpful. But I want to move to the SymPy and the Python stuff, or maybe I don't know, maybe with Qtip. I don't know. I've never used Qtip either. Anyway, so that's a bit of the background. And then I found this yesterday, mathisfun.com, which seems to the page doesn't look like looks a bit weird, but so there's some techniques. I don't know if these are all, but we can go through some of these. And then I'd love to do one. I'd love to try to attempt to do one today. Like, I don't know, one exercise. Uh, The thing is, I'm not well set up. I don't have this well configured to work with my two screens, so I will see how I will get that done with Paint. But anyway, so something to do, we need to solve it. So we know the answers are functions or sets of functions that satisfy the equation. There's no magic way to solve. Um, but over the millennia, great minds have been building on each other's work and have discovered different methods, possibly long and complicated methods of solving some types of differential equations. Good. So separation of variables. So I think each of these expand to a separate chapter, right? Yeah, here's the method. Oh, and an example. Rabbits. More examples. Are there exercises? That'll be cool. Oh, okay, but I could okay, so I could just take one, pick one, and then see and look at these, right? And then kind of don't look at the solution. We could also do that. So I will not go through all the examples, but first I want to just go through some of the methods, and then we'll pick one and try to do it. So when can we use the separation of variables? So can be used when all the y terms, including dy, can be moved on one side, and the x terms, including dx, to the other side. Okay. Step, move all the y terms, including dy, to one side, the x terms to the other side, integrate one side with respect to y and the other side with respect to x. What? Why? Oh, yeah. Sorry. Yeah, obviously, because you have the variables in each side. So you just do the integration. Don't forget the plus c, the constant of integration. Oh, yeah. So when you're integrating, say, 5 with respect to x, right? The if you integrate that, you should get 5x plus c, right? Because there could be a constant that obviously could be 0, but it doesn't have to be. And then simplify. Let's take a look at an example. So the derivative of y with respect to x is k times y. So we separate the things, and so we get y down here, x there. Integrate both sides. So you do the integral of, I guess, this is 1 divided by y, and this is k. Oh yeah, the plus c is always there. So the constant has to always be there. So that's the natural logarithm of y. I don't remember I really don't remember. Is there a cheat sheet? Integrals? Uh, integrals cheat sheet. Properties, common integrals, something like this. Come on, do I have to click so much to get somewhere? I hope it's not going to ask me for my email. Okay, cool. So, why is that slow? Oh, screw you. I just want like a. I just want like an image. Can we just have an image? Can we just have a normal image? Oh, there you go. Derivatives and integrals, common integrals. So k is kx plus c. Yeah. So 1 divided by x is the logarithm of x plus c. Okay, so these are common integrals and then trigonometric substitutions. What? I don't know what this means by substitution, approximating definite integrals, common derivatives. Okay, cool. Anyway, yeah, this is one of these things where you gotta just memorize in school and then you forget if you don't use these. But you integrate that and you get these, and so so you get that expression. C is the constant of integration, and D we use D for the other as it is a different constant, of course. And then simplify. So we have, okay, so we can roll the two constants into one. Yeah. So d minus c. And then you have the logarithm of y is k times x plus a. Oh, I'm so rusty with these kind of stuff that like I would never have guessed that you can do that. But yeah, I mean, you want to get the y out from the logarithm, right? Because you want this to be expressed as a function, so of y as a function of x. So you take exponents on both sides. So e to the power of logarithm of e, the natural logarithm. Is this ln the logarithm in base e? Oh yeah, there you have the natural logarithm. Oh, okay, cool. So you simplify, and then you yeah, okay, so these I know you can do the these times these, right? And then, well, that is another that is another constant, right? And yeah, that's it. So that's the function you have, and so you've solved the differential equation. Okay, cool. So just basically, if you can separate these things, and I guess that works also for like higher degrees, right? So it doesn't have to be just the 1 degree, sort of the first differential. Like it just be also the second derivative of y. Okay, that maybe. Yeah, okay, but I get that. So that's and I will not do I will not do examples now. We'll go through examples later. First order linear. First order linear differential equations. So of this type, derivative of y over x plus px. Okay, so these are functions. So this is px and qx are functions of x. Functions of x. Okay, they are first order when there's only, yeah. Okay, so it's only the first derivative. It's not the second or the third. A nonlinear, so this is a nonlinear differential equation is often hard to solve, but we can sometimes approximate it with a linear differential equation to find an easy solution. Okay. But how do we solve these? So these we read. Okay, so to solve it, there's a special method. We invent two new functions of x, call them u and v, and say that y equals u times v. Okay. We then solve to find u, and then find v, and tidy up, and then we're done. But why you do that? And we also use the derivative of y. See the product rule. Oh, because the derivative of these is, because the product rule is that the derivative of these is the sum of, right? Derivation rules. Product rule. Yeah, so the function f times g is the derivative is f times the derivative of g of g plus the derivative of f times g. So you, okay, so you use the product rule to say, yeah, because it's linear, right? Or because you've got these functions of x, right, as expressed as a sum, then you can imagine that there was but why this is why. Not sure I understand this completely, but let's see. Step-by-step method. So substitute y equals u times v, right, into these. Factor the parts involving v, put the term v equal to 0. This gives a differential equation in u and x, which can be solved in the next step. Solve using separation of variables. To find u, substitute u back into the equation, solve then b, and then you got the solution. So maybe let's just look at an example. Okay, but couldn't we just use separation of variables here? Couldn't we just use separate? No, we cannot use separation. Couldn't we just use separation of values directly here? Like you move this term here, 1 plus y divided by x. Yeah, okay, no, but I get it. You can never, yeah, you cannot separate those. You won't, because of the constant, you won't be able to move y back here, or yeah. Okay, so then you make up, so then you kind of make up that, yeah, you say, okay, so so that's the form. So q of x is constant, and then here p of x is minus 1 divided by x, of course, times y. So how do you do this? So you substitute y into these, right? So you say, so these becomes these. So you replace this part here for this one here, and then factor the parts involving v. I see what I see. So wait, SQL. Why do we do these? Term v term equal to 0. So solve with the expression of values and solve to find v. Separate variables. And then substitute y equals uv to find the solution to the original. So there's a few steps that I don't understand here. I understand how to identify this, I understand the form, I understand, I think. So why can you say that y equals u times v, right? So u is what? Two new functions of x, call them u and v, and say that y equals u times v. Why can we do that though? Why can we, I don't know why we can do that. So how do we know that y is of this form? Let's see if we can find it somewhere else. Math is fun. Again, I'm not gonna watch videos because I haven't yet figured out how to route the the sound correctly. I will do though. The most general first order differential equation can be written as these. Oh, but that's like, I think that's 2 dimensions, or 2 variables, but doesn't matter, right? But yeah, okay, so this is what we have. A of x and f of x are continuous functions of x. 2 methods, using an integrating factor and method of variation of a constant. So I think this comes later. I think this is what we've been doing. If a linear differential equation is written in the standard form, the integration factor is defined by the formula. No, that's not the technique. Give me. Good. um, okay, so there's a bunch of methods actually. Integrating factors. Oh, but maybe this is it really. No, it can let. So that's another technique. Okay. Separable. Uh, so what the fuck is this method called? I cannot seem to find. So why? Like I don't understand why you can do that in the first place. Why can you do that in the first place? Um, is this the integration? Okay, this is the. This seems to be so. This problem is given in the G.F. Simon's book on differential equations, page 9. I'm confused here. U and y are supposed to be dependent on x. So how am I supposed to differentiate these and replace derivatives of y and get only the differential equation in v? So u and v are functions of x. You're factoring y as a product of 2 functions. There are a lot of such pairs. Then you're free to move through the space of such pairs until you find a pair that happens to make all of the v's cancel. in the equation. What? Okay, so you're just making it up. It can be that it doesn't. It can be that it doesn't work, right? If y cannot be factored, it could be, right? So here you're just kind of giving it a try. So you're saying, okay, so y is a factor of two new functions u and v. So you replace. Okay, so let's assume that this doesn't have to always work, but so you replace y by uv by here, right? So you get these first of all, n into here, right? So you get this chunk in here, and then you get u times v here. Well, let's do it again with the example, right? So you have this function, then you define uv. It turns into, so this is the stuff there, and then okay, and then you replace y by uv divided by x, and then this is 1. Okay, so I get that, how we get here. Now we factor the parts involving v. So we factor v out. How? Oh yeah, because it's here and it's here. So we factor these v. Cool. So now we have u times the derivative of v with respect to x, and v, and these are functions, right? Yeah, because that's the product rule. Okay. Yeah. Put the v term equal to 0. Why do we do this? Why do we do this? Then suppose so back to the equation. So then the derivative is this. Okay, no, that's too complicated because that's the second order. But then it says, okay, so okay, so they do these, right? And then you have the u terms. Then suppose, why am I doing these? Am I just also doing it just as an attempt to find? So u and v are functions of x. You're factoring y as product of functions. A lot of such pairs. Then you are free to move through the space of such pairs until you find a pair that happens to make all the derivatives of v cancel in the equation. So making the substitution, you obtain these. So all we need to find is a pair of v and v such that 2 times the derivative of, so such that these plus these equals 0? Why? So I don't quite get why that. I mean, okay, so that is just it seems to be just as like again like an attempt to do that, right? So it says here in the general method, it says put the v term. I know it says put the term v equal to 0. This gives the differential equation of u and x, which can be solved in the next step. So I guess what if this doesn't work? Hmm. Hmm. I don't understand this. So I understand that you can make it up, but I don't understand why you got to factor the parts involving v, and why you put the v term equal to 0. Mm, but okay. So this is the, so here I don't understand that part. Let's just go ahead. Maybe it'll become clearer later. Homogeneous equations. Where's the timing? Okay. Homogeneous differential equations look like these. We can solve them by using a change of variables. V equals y divided by x. Okay. So what this says is new variable v equals y divided by x. Yeah. So you also have the derivative, so you can also simplify. Okay, so yeah. So you simplify. So you put these on one side, a function of y and x. Okay, so if this is yeah, so that's an example, and then you have. Can we get it in y divided by x style? So start with these, separate the terms, simplify, reciprocal of first term. What? Ah, okay, yeah. So now you have of y divided by x. Do you? Okay, so it's got to be in this form. Why you cannot generalize that though? Uh, oh, because then we know we can apply the product rule. That's why, right? Because the derivative of y with respect to x in this case is this. So that's why we can solve it. Okay. Boo. That looks all super complicated. Okay, so you replace so if all these methods they feel so random. So for you to apply these, you need to um, make sure you can express that in this style. A function of y divided by x. And only in this case we can do so we do that and so we say okay so that's the same like saying y equals v times x. Okay, so all what this means is you got to make sure that you can express y as a sort of x times what? Okay, so here I'm not sure I understand why this form must be why you cannot just do this with any form. But let's see what else we have here. Um, Bernoulli equation. So of this general form, and is a real number but not zero. Okay, so these techniques are pretty sick, man. So what is the form? So the derivative of y with respect to x, then function of x times y and function of x times y to a power. Yeah, okay. So if it's 0 or 1, it can be solved with the as a first order linear differential equation. A separation of values. Okay. What you can substitute by having a substitution u equals y to the power of 1 minus n. Turning it into a linear differential equation and then solve that. Oh yeah, because then you have like u times y. So you have these, right? And then yeah, p is x to the power of 5, q is x to the power of 5, and then we have these. So you replace that. Uh, Wait, what? So u equals y to the power of 1 minus n. So u equals to y to the power of minus 6. In terms of y, that is y equals u to the power of minus 1/6. Mm, yeah, we differentiate y with respect to x. So you've got these. Okay, so essentially I see that what you're trying to do a lot of times is just find an expression with just substitutions that allows you to do the differentiation so you get rid of these terms because that's what's bothering in the equation. So you have that and then substitute this in the original equation. Multiply all terms by These? What? What? Yeah, this is way. I'm almost thinking I almost kind of have to do just like one dedicated sessions for each of them. I mean, I won't bother you with a lot of these, but I definitely want to do some practice. Substitution works, so we now have an equation we can hopefully solve. Separation of variable of variables. Why weren't we able to do that before? Because we couldn't separate the variables. Okay. But how did that make it easy to separate any variables? I don't understand that. So so now we have this form. Okay, so these so what this is doing is this is turning it into an expression that you can use separation of variables with. So this separation of variables turns out to be always sort of the core method. You're trying to simplify it down to that point. Because basically here you can factor things out. And so now you have that. Like these, you cannot just, well, in theory you could, right? Why not? Why can't you solve these with separations of variables directly? Let's try. Maybe let's use that as an example. Probably fail, but so yeah, but that just works as shit, so I don't know what to do. We'll get pain. So we'll get these here, we'll get these here, right? So we have these here. So we have, I'm almost thinking, oh God. So we have, um, so we have these, right? So we have, so I could move that to the other side, right? And we have dy divided by dx equals x to the power of 5 times y to the power of 7 minus x to the power of 5 times y. And I can factor the x by just saying, you know, that this part is equivalent to like x to the power of 5 times y to the power of 7 minus y, right? And that equals to, you know, these. And then I can just say dy divided that by y to the power 7 minus y equals x, no, one, so 1 divided by x to the power 5. No, what? Ah, what? Sorry. What am I doing? No. So I have the x to the power 5. That's it's just I confused that. I'm stupid. I confused that with the division line. Times dx, right? Is that like just separation of values? Then I can just integrate each side, right? And so this side is obviously uh, I think that is, if I remember well, so well, that would have been something along the lines of these, right? Because the derivation is you put that exponent down and you minus this one, right? I think that is correct. Where do I have my cheat sheet? Uh, what? I cannot see the full thing. Oh yeah, look at this. So this is this thing here. So x to the power of n, and so here is 1 divided by n plus 1 times x plus, uh, what? Oh crap. What does it mean plus c times n doesn't equal minus 1? What the fuck is that? So integrate um, x to power of n, something like this. It's a basic one, but I think that's, can that render well? Or can I think, oh, yeah. Yeah, okay, but there's no constant then? There must be the constant, right? Yeah, but that's correct. So, okay. So, that seems to be correct. Now, how do I integrate these guys here? Well, I could do, so I could split, because so this is obviously 1 divided by y times 1 divided by y 6 minus 1, right? Because I can factor 1y out. And so if I have this, and I can integrate these. Can I integrate these easily? So what does the cheat sheet say? Integration of, well, is there any kind of product rule here that we could use? Properties, no, that's a constant. Integration of yeah, well, but I could always redefine. I could always redefine. No, can I redefine? I probably cannot redefine. No, I cannot redefine, I think. Because, no. A squared plus u squared. Uh, or I can integrate by parts. Can I? So u times v minus the integral of would that work? But in this case, so what this is telling me is that I could just integrate. Yeah, maybe that might as well just work, right? So what was that? Integration by parts. So that is, if we take these, right, this form, so u times v minus the integral of v du. Or I don't know. Can I use that? Can I just use that minus? So u times v minus v du. So what? So you'd say u times v, right? So u is u times v. That just basically say, take that whole thing out, and then it's like, what do we say, minus the integral of what, y d. Yeah, that's weird. No, that's not, that doesn't make sense. Rusty at this stuff. How do you solve this integral, man? I don't know. It's none of the common ones. None of the common ones. Maybe that's why it doesn't work. Can I cheat and ask Wolfram Alpha? I think you have a integral calculator. So integrate. So what do you have to give it? Just the, okay, integrate 1 divided by y 7, right? Minus y. Does this work? Yeah. Oh, Jesus, that's complicated. But it could be. Okay, so a complex value logarithm. What? What the fuck is that? Assuming y is positive. Series expansion. Okay, so you would have these, But then you want to take the logarithm. Yeah, that's complicated. Okay, I see. Then you want to take the y's out of that logarithm, and that's just if it's possible, this is going to be complicated. So, but maybe it's doable. I don't know. Yeah. So that method. So that's why. What was the one that I was doing? This one. So that's why this method is better. Why? Because you get a so these are easier to integrate. Okay. But wouldn't I cheat sheet. Cheat sheet. Okay, ax plus b. It's gonna be of this form. So then you can actually replace it with a logarithm. Yup. Okay. What am I doing? Sorry. Um, so okay, so these are okay. So I don't, yeah, understanding the different methods is not that simple, right? Or why do they work? But there's a bunch of methods. So you've got these here. So in this specific case, there's a substitution that it just makes the separation of variables easier because you could attempt that directly, but as you've seen, then you end up in a mess. Um, man, yeah, but that's so when you have these, because I guess what these car, I guess what you're trying to do is you're trying to, um, so you're trying to get to a point where one of the components doesn't have that exponent, right? If y wouldn't have that, that's why they say that if n is one, then you can just do separation of values of variables, because that's what's bothering, right? Is this is what's bothering is that you're gonna have when you try to separate the variables, you're gonna have that high exponential in there, um, which if you try to redefine and invent that u like these, that is going to um, mhm. That is gonna allow you to do this replacement here and this replacement here where you're plus 7. Not plus, it's times 7, so you have like minus 7/6. Yeah, so you get rid of these because the derivative has the same term. Okay, that's pretty smart, I get it. Because, yeah, okay, so you do that so that you can have an exponent on replace these with the derivative, obviously, which kind of has that exponent, right? And because you then have that exponent in both ends, you can actually, by doing this multiplication on all the sides, you basically, yeah, you just basically kill that exponent. You couldn't do that before because you just have dy of dx, where you just don't know what that is, and so okay, so that's the goal here, is to kind of kill that exponent by doing that, and it does not always work probably, right? Um, and then you have an easier one to solve. Okay, so this I understood. That's a good technique. These I still don't understand why the equal thing to zero. Maybe I can try to understand that a bit more, because I mean this I get why this works. Okay, this is also not completely, but yeah. So the different techniques, and then what else is there? Second order equations. We'll leave that for another day. But I guess a lot of the tricks is going to be to try to approximate it with the first order because they're easier to solve. And determine coefficients. Okay, so variation of parameters. That seems to be start with the general solution. Okay. Nuts. That looks like nuts. The Ronskin. The Ronskin. What the fuck? Oh, Vronskin. That's like a Polish name. Okay. Vronsky. Ah, cool. Jesus. Yeah, but are these all? Like, I don't think that these are all right. So this is just some, okay, so there's ordinary differential equations versus partial differential equations. Super methods to solve them. Okay. So, but I guess, so I guess all what these techniques are doing is it's always trying to always reduce this to something simpler. Maybe with the exception of this one, but something you can solve with separation of variables and stuff like that, because techniques to solve PDEs. So there's some numerical methods. The method of lines. The, Jesus Christ, that looks like crazy. And software, okay, so then you're getting into software land. Numerical techniques. So the numerical techniques, right, are just basically, okay, so you just approximate that by just trying solutions, I think, right? Gradient discretization, finite volume method, spectral method, mesh-free method. This is complicated stuff, man. But okay, so this gets quite nuts. Okay, so next session. Oh, so hi, I just saw now the message in the chat. You can solve linear differential equations from any order with an exponential function. Uh, yeah, I see. I saw. I think I was, but I don't know. It's funny that it's not here in this page. But I saw the. I came across this method. Maybe we can just focus on this next time. So, where was that? That's what you mean, right? I think you can do that. There's a method that is not in here for some reason, that is for differential equations. So solving differentials, it's a linear equations, and I think that second order case. That's probably what you mean, right? I guess. Okay, so we'll try that next time. I think I've got a fairly good idea of this topic. Just haven't enough time today to dig more into these, but so if there's so this, I'll just look for these. So there's you can solve from any order with an exponential function. So I just really want to find something so I don't have to spend time looking for this next week or next time. Try to get something done before. So so I think I think that's probably what you mean. It's PDF. Yeah, that's probably for constant coefficient linear ODE in the case of this form. Solutions can be easily obtained without working backwards from the solutions. The first step is to compute the roots of the characteristic polynomial. No, maybe that's not what you mean. Damn it! I just came across these, I think. Like literally like 10 minutes ago. Why is it so hard to find this stuff? So solve linear. Uh, mm, mm. Access denied. Service unavailable in the EU region. Go fuck yourself. Oh, I think it was this one maybe. Oh yeah, I think that is. Yeah, yeah. There you go. There you go. I think that's what you mean, right? So you with these, so it says the differential equation of this type, continuous functions using integrating factor. So if a linear differential equation is written in the standard form, then you can integrate. Then the integrating factor is defined by this formula. So you define a u a new function u that is it's e to the power of the integral of ax. So this part here. So if you multiply the left side of the equation by the integrating factor, it converts the left side into the derivative of the product. Whoa, 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 whoa. And so you multiply the left side of the equation by the integrating factor. Um, you mean, why would you do that though? The general solution of the differential equation is expressed as. Okay, I'll get to these, but I guess that's what you mean. I guess that's a solution, but that's a technique you mean with the integrating factor, with this exponential. And there's also the variation of a constant. Okay, cool. But damn, these are hard things. These are complicated. This is complicated stuff. Um, and now, so but what I take out of these is that it seems like uh, it seems to me right the at least a type of a version of the Schrodinger equation should be solvable just by the fact that we know what form a wave function has, and so that could allow us to replace maybe that in there and then try to solve for these. Maybe that is at least for the quantum harmonic oscillator case, we could try that. But I want to spend some more time. I want to dig some more into differential equations and kind of feel more comfortable with them in general. And then try to do some examples. I just have to set that up correctly. Good. That's hard, but we'll get there. Stay safe and have a good day.